Okay, so let us start. So yeah, so I hope most of you are here. So today we are going to talk about this notion of sectional curvature, and the lecture next week is going to be on Ricci curvature, a little bit of Ricci curvature, and what's called scalar curvature. So what I would like to emphasize among the two lectures is that this is, in my opinion, sectional curvature, when you're learning Riemannian geometry for the first time, is perhaps the more important concept to wrap your head around, and also the more important section from the point of view of the course and the exams and so on. So I would say focus more on lecture 27 and be aware of what goes on in the next lecture. But lecture 27 is sort of, in some sense, more fundamental. Okay. So we're going to talk about what's called the sectional curvature. So sectional curvature is something which was originally what Riemann was looking at, motivated by Gaussian curvature, and then these collection of sectional curvatures arranged in the specific form led to the formulation of the Riemann curvature. So we'll get to there, but before that, let us start with some linear algebra. So you have an inner product space, which means it's a vector space V, it's over the reals, and typically we're going to assume V is finite dimensional. Inner product means that there's an inner product which is symmetric, positive definite, and it's a map from V cross B to R, which is bilinear, correct? So if you're given two vectors V and W, you can consider this expression. Okay, this is a notation, and just keep this notation in mind because this is going to be used in all the subsequent lectures. The absolute value of V wedge W. Okay, so this is, so V and W are vectors. So V wedge W doesn't really make sense unless you think of V wedge W as an element of wedge 2 of V. Okay, but this is just a notation. V wedge W, whatever this object is, absolute value of that is by definition this number, square root of mod V square mod W square minus inner product VW square. And by Cauchy-Schwarz inequality, we know that this thing inside the square root is a non-negative quantity, so the positive square root exists. Okay? So this absolute V wedge W is a non-negative quantity. Okay? But what is this quantity? I mean, this is something you have seen in linear algebra, you have seen in functional analysis, you have seen in all sorts of places, in geometry, in physics. So what geometric thing does this number represent?
It's the volume of the parallelogram between V and W, the area of the parallelogram.
Yeah. So here V and W are just two vectors. So you just take the plane spanned by VW. It could be a line if V is a scalar multiple of W, in which case this is obviously 0, the inside, because V dot W would be just that. So this is exactly as Ujan said, this is the area of the parallelogram without a sign, because it's a sign, it's not the signed area, it's just the absolute area of the parallelogram determined by V and W, right? Okay, good. So why is this relevant? Well, we are soon going to see why it is so. So we want to define the notion of sectional curvature. What do we do? Well, we take a two-dimensional subspace of a tangent space, okay? So I know some of you might end up making this sort of error when writing things down in a hurry. A two-dimensional subspace of the tangent bundle TM does not make sense. But a two-dimensional subspace of TPM, of course, makes sense. So this is for a fixed point P in M. Look at the tangent space, look at a two-dimensional subspace sigma, and choose any basis x comma y for sigma. Okay. Now you define the sectional curvature of the two planes. So this is a notion associated to a two plane inside the tangent space of a point. So strictly speaking, this K sigma should ideally be expressed as Kp comma sigma. So this is the sectional curvature of the two plane contained in TPM. And I'm defining this sectional curvature to be this quantity, Kx comma y. But Kx comma y is by definition the Riemann curvature tensor Rxy. So we have seen what this is last time, right? This is simply going to be extend xy to vector fields on M, then take nabla x, nabla y acting on x, minus nabla y, nabla x acting on x, minus nabla Lie bracket xy acting on x, and then dot the whole thing with y. Okay, so I mean, it should be clear. We have spent a lot of time about this. What the numerator is? The numerator is simply this these things we were calculating last time, Rij, things of that sort. Okay? So it's that Riemann curvature tensor at the point P, and you divide out by the area square. Okay, so
Sir,
yes,
since sigma can have many bases, this thing should be, this k of xy should be independent of the basis,
we'll
because
get there. Yeah, we'll get there. So yeah, just hold your thought for a minute. So this is how a lot of things in math are often defined. You define it using a choice, and then of course you have to show that it's independent of the choice. Okay? But let me define this first. So you define k of xy to be this quantity. It's a Riemann curvature, but it's normalized, because if you scale x and y by 2 and 3 respectively in the Riemann curvature, you basically get 2 into 3 into 2 into 3. So obviously kxy is not independent up to scaling if I don't have the denominator, which is what controls that if I scale x by lambda and scale y by mu, kxy and k lambda x mu y is the same. Okay? So anyway, so it's this normalization. So in particular, if I choose an orthonormal basis for sigma, then the area of the parallelogram is 1, so the denominator just vanishes. So it's just 1. So it's just the usual Riemann curvature R xy xy. Okay, right. So now coming back to Swapnil's question, so we define the sectional curvature of sigma in terms of a basis. So how do I know that this is independent of the basis? Well, you first of all observe that kxy is symmetric in y and x. Right? If I switch x and y, what happens? Well, if I switch x and y, I get rp yx, but that is the same, okay, because of the usual symmetries of the Riemann curvature tensor. And the denominator is the same because the area of the parallelogram spanned by x and y and the area of the parallelogram spanned by y and x are identical. So K has this symmetry, okay? So what about something like this? Is it clear that Kxy is K lambda x y? See, what would happen if I input lambda x y in R in the Riemann curvature? Because it's tensorial, lambda square is going to come out, right? In the numerator. What happens to the denominator? Again, lambda square is going to come out because x is going to get replaced by lambda, but that means you get lambda square and then absolute x wedge y whole square. So the lambda square cancels. So K also has this extra property that if I scale any one of these entries, x by lambda or y by mu, it's the same old K. That's what this area of the parallelogram was designed to do, right? We have one more quantity, which is this. Kxy is equal to K of x plus lambda y comma y. So again, this is clear because if you look at the denominator, what happens to the area of the parallelogram spanned by x plus lambda y and y versus the parallelogram spanned by x and y? Are their areas the same? This is almost like a high school geometry question. So you have drawn all these things. So remember, whenever you calculate the area of a parallelogram, it's the base times the height. So the height is the only thing that matters. Your parallelogram could be slanted as much as you want, as long as it has the same height and the same base. The areas are the same, right? So this slanting is exactly taken care of by adding lambda y to x. So the numerator of kx plus lambda y is exactly the same as the numerator of kxy. That's just saying that the areas of two parallelograms with the same base and height are the same. And the denominator is also the same, okay? Because when you calculate, the denominator is the same because of the area of the parallelogram thing. And the numerator is the same because we have seen that whenever you have two repeating indices in the first two slots or in the last two slots, the Riemann curvature is 0, it's skew symmetry. Okay? So this is something that you should be absolutely okay with because we talked so much about the symmetry of the Riemann curvature. So K satisfies all the three properties. Okay? So now, armed with these three observations, you can show that K sigma is indeed well defined, meaning it does not depend on the choice of the basis xy. And the reason being, if you choose any other basis x prime and y prime, you can express x prime as a combination of x and y prime as a combination of x and y, and then simply use a combination of these three properties to conclude that kx prime y prime is kxy. Okay?
So I have one question, perhaps a bit naive. I mean, so for one-dimensional manifolds, there is no question of there being a two-dimensional subspace of TPM.
Yes. So so the Riemann curvature is 0. So you might say that, okay, if it's a curve, then I mean, okay, my guess is that you're probably thinking of curves inside, say, R3 or R2, and then that has a curvature. So how is that what you're asking? How is that curvature related to this?
Yes, kind of.
So this curvature, of course, doesn't make sense for one-dimensional manifold. Okay. So I mean, in this tensor sense. So if you think of an embedding, then of course that curvature is the embedding of a curve inside something else, and that curvature, that 1 over r square or whatever you calculate, that is basically how this one-dimensional manifold is embedded inside something else. But here we are talking about an intrinsic manifold M itself, and we are not saying embedded inside something. This is just a manifold on its own. And once you
Okay.
put a metric, it's asking for what are the curvature of the manifold with the metric that you imposed on it. And so from that point of view, if you want to say what happens to a one-dimensional manifold, well, we have seen that for an abstract one-dimensional manifold, it's a curve and it can be parameterized by its arc length. Okay? And anything can be
Yes.
parameterized by arc length. So once you do that parameterization, there's no other information that you have. Everything else is taken care of.
Okay.
An abstract one manifold. So that curvature that you have seen in curves and surfaces is not exactly this curvature, simply because that is taking into account that that one manifold cannot live as itself. It has to live inside some R3, and that map, how it maps that one manifold inside R3, will say how bent it is.
Okay.
But this is sort of intrinsic to M itself, that given M as an abstract manifold, given G, you define this to be the sectional curvature. So, yeah, so it doesn't
Thank
make sense for one-dimensional things. It's going to be 0 because
oh,
of the obvious reason.
oh.
Yes. Okay.
Okay. Thank you, sir.
Okay. So yeah, so I hope this exercise is okay. So I've done most of the hard part for you. Use these 3 things in a combination and show that K sigma is well defined. Okay. So this is a good definition now, because this says that, okay, you to compute the sectional curvature, you just compute it for an orthonormal basis, so that you don't have to calculate the area of the parallelogram. It simply becomes Rij if xi xj is an orthonormal basis at the point P, right? Or del xi del xj is an orthonormal basis at the point P, and that's what we're going to do in a lot of the examples later on. Okay, is it clear? So this is what the sectional curvature is. Okay, any questions? Okay, good. So let me move on. So of course you might want to start with the basic example of a surface. You might say, think of a surface, not just in R3, but an abstract surface. What is the notion of sectional curvature? Well, it's saying choose a 2-plane in TPM, but TPM is itself a 2-plane because M is 2-dimensional. So the only 2-plane that you can choose is TPM. So the sectional curvature for a surface at a point is something assigned to the tangent space. And if you see the definition, you'll see that if x and y was an orthonormal basis, this is precisely the Gaussian curvature, because R1212 was the Gaussian curvature, as we saw in the last lecture, right? So the sectional curvature for surfaces is the Gaussian curvature. Nothing more, nothing less. Okay. Okay. What about higher manifolds? Well, higher dimensional manifolds, this is a generalization which is adapted to higher dimensions. Okay, simply because now you cannot talk about a curvature assigned to the tangent plane, but you're assigning a curvature to every 2-plane inside the tangent plane, and the point P, of course, will vary. Okay, so the sectional curvature really is a number. It could be negative, it could be positive, it could be 0. It's a number assigned to a 2-plane, to all 2 planes inside TPM, and P also varies. So see, there's a footnote down below. I'll explain that when we get to, but for those of you who have seen Grassmannians, fix a point P, look at TPM. That's an abstract vector space of dimension n. What are we saying? We're saying the sectional curvature takes in any 2-plane inside TPM, assigns a number. But the collection of all 2 planes inside a vector space is nothing but the Grassmannian of 2 planes inside the vector space V. So the sectional curvature is basically a function on the Grassmannian of 2 planes in TPM. But P is allowed to vary as well. So as you vary P in M, you're basically looking at TPM, looking at the Grassmannian 2 planes inside TPM and letting P vary. So this itself will form a bundle. It's not going to be a vector bundle, but it's going to be a bundle where fibers are Grassmannians, and it's called the Grassmannian two-plane bundle. Okay, for those who would like to read about this more, I mean, you can look up. That's why I introduced the terminology. But we are not going to make use of that for our lecture, okay? Because for the most part, yes.
So, sir, in physics, we had studied about Grassmann variables and Grassmann algebra. So, anti-commuting. So, it's about variables which anti-commute. So, what do you mean by Grassmannian here? Is it somehow related to Grassmann algebra?
So, as I said, there might be some relation, but not in the variable sense. So, here Grassmannian is a concept that if you look at the collection of all two-dimensional subspaces inside a vector space V, it turns out that's a manifold on its own. Okay, so that manifold is usually called the Grassmannian of two planes inside V. That's just a name. Okay, so
Has it something to do with Grassmann algebra?
not really. So see, these are manifolds. So these are not going to give you any algebras even at the tangent level or otherwise. But it must be that I don't know the history of how the nomenclature of the other thing happened. So this is called Grassmannian of K planes inside V. Okay, so as far as I'm concerned, there's no connection between the anti-commuting variables because this is just a manifold. You choose a vector space V, you choose all the K planes in V, and that turns out to be a manifold of a certain dimension, and you call it the Grassmannian of K planes in V. That's it. It's a manifold. It's often a complex manifold and all sorts of things, homogeneous variety and so on. But it's not any kind of a group or any algebra of any sort. But just a name. I mean, there's no reason for them to be identically the same thing. Right? So this is just an object that you can construct, and this is really where the sectional curvature lives. That's my point. If you don't like this, then think of sectional curvature as a pointwise thing. For every two plane in TPM, it's a number. But it is really a function defined on this big gadget called the Grassmannian two-plane bundle of TM. If you want to study this, but for obvious reasons, you probably don't want to study this because this is, like too big a gadget. So, but this is where the definition happens. Okay. Any other questions? Okay, so the Euclidean space is our first example for obvious reasons that we consider Rn with the flat Euclidean metric. And I'm saying flat now because we have introduced what flat means, and we have shown last time that Rn with the Euclidean metric is flat. Okay, so flat again means that Rijkl is 0, and here you can choose xi's to be the global coordinates, and from that, of course, we conclude that k sigma is also 0 because k sigma is simply going to be Rij divided by 1 because del by del xi and del by del xj are already perpendicular. But all the Rijk is 0, so the sectional curvature is 0 for any two plane. Okay. So, and for any point P. So this says that Rn with the standard Euclidean metric has constant 0 sectional curvature. All right. So yeah, so this was the point that I was saying earlier, that the sectional curvature is strictly speaking a real valued function from the Grassmannian of two planes in TPM. But P is now allowed to vary, and this whole thing can be combined to form what's called the Grassmannian two-plane bundle. That's a bundle over M, where the fibers are Grassmannian of two planes inside a vector space of dimension N. I mean, this is more of a comment for people who might read more of bundle theory and gauge theory later on. If you haven't seen those things, do not have to worry. Just take it as an abstract quantity. This is not going to be relevant for our computations. Okay. But the real question that you should ask is, we took the Riemann curvature tensor, which had 4 indices. We somehow passed to the sectional curvature. And sectional curvature seems like a weaker information because you're using the Riemann curvature to deduce the sectional curvature. So the question really is, are we losing information by working strictly with sectional curvature? Okay. And the next lemma addresses that, saying that actually not. The sectional curvature determines back the Riemann curvature tensor. So they have the same amount of data. Okay? But sectional curvature, as you can see now, is geometrically much more easy to interpret and often easier to calculate in local coordinates. So this is a much more amenable thing to work with. Okay? So this is the lemma. The sectional curvature determines the Riemann curvature. So let me point out that this is the proof, rather, is essentially an algebraic fact. And this really uses, crucially, the symmetries of the Riemann curvature tensor. And this is a lemma which is true for any curvature tensor or any kind of a 4 tensor or a 4-1 tensor. Like it takes 4 inputs, it's tensorial, which has the same symmetries as the Riemann curvature tensor. I mean, it doesn't have to be the Riemann curvature tensor. That's my point, as you'll see in the proof, that it's really an algebraic fact. Okay? So let's go on to the proof, and you'll see what I mean by algebraic. Okay. So fix 4 vectors x, y, z, w, and unfortunately, I'm not going to put x, y, z, w in the alphabetical order. I'll be putting it in this order, x, y, z, w, because I want x, y to be my first 2 variables typically. If you're reading Docarmo, then Docarmo uses x, y, z, t, but I don't want to use t because I'll be taking limits at various places, and I want t to be the variable associated to limit t goes to 0. So hence, I'm choosing x, y, z, w, but w will come after z. Okay, this is just maybe not aesthetically the most pleasing, but you know, not everything has to be. So okay, let's consider this function of 2 variables s comma t. These are real parameters, and you define it to be this. Okay, just take a look. This is x plus sz, y plus tw, followed by x plus sz, y plus tw. So this quantity here, the left hand side, this is essentially up to a scaling the sectional curvature, right? Because it's x plus sz, y plus tw, and the same thing repeated. The second term here, that is also up to a scaling the sectional curvature. It is x plus sw, y plus tz, followed by the same thing, x plus sw, y plus tz. So this quantity up to the relevant scaling is determined by the sectional curvature, right? So if I know the sectional curvatures, I can multiply by the area of the parallelogram, and then I can combine it in this form. So f of s comma t is a function entirely determined by the sectional curvatures, which we're assuming we know. So how do I get the Riemann curvature back? Well, I have to calculate r, x, y, z, w at the point P from this. Then I'll be done, because x, y, z, w, and P was arbitrary. This recovers the Riemann curvature tensor, right? So what we do is we basically expand this. See, this is going to be typically a polynomial because of the obvious reason. You can expand using linearity in all the 4 slots. And we only care about the term, which is the coefficient of st, because this is going to have some terms, the 0th term, the linear term, the quadratic term. In the quadratic term, there are going to be terms of the form st times something. So that's what we want. So is that clear? So expand this as a function of s and t, and in that you try to look for the coefficient of st. Okay, so how do I get that coefficient? Well, I first take df by ds, set s equal to 0. What I get is going to be something having only t and r of x, y, z, w, and then I take d by dt. So if I want the coefficient of st, I basically take del f del s, del f, del 2f by del s del t, and set s equal to t equal to 0. What I recover is precisely the coefficient of st, and that's what we're going to do. So we first take the partial derivative of f with respect to s, and set s is equal to 0. And I leave it as an exercise. You can simply expand this, use the linearity of r in all the 4 slots, and show that the partial of f with respect to s is twice of this Riemann, this Riemann curvature minus twice of this Riemann curvature. So these 2 Riemann curvatures can be deduced from f, which can be deduced from the sectional curvatures. But these 2 Riemann curvatures are not sectional curvatures themselves, because it's x, y plus tw, z, y plus tw. Okay, so this is not a sectional curvature, and neither is h of t. But this is an easy exercise. I'd ideally want all of you to go back and do these couple of lines computation. So this is the first partial that we want, del f del s. Okay, let's call these functions g of t and h of t. So any questions so far before we move on? Okay. So what do I want? I want to take del 2f by del s del t. So what would that mean? I have to calculate g prime of 0 and h prime of 0. That's what del g del t means, right? Because g is a function of t, h is a function of t. So what is g prime of 0? Well, it is simply g of t minus g of 0 divided by t, limit t goes to 0. So what is g of t? Well, it's exactly what you have up here. That's this. What is g of 0? Well, g of 0 is r of x, y, z, w. Yeah, so there's a typo here. This should be a w, okay? Let's make that note here. The last term, r, x, y, z, y, that's r, x, y, z, w, obviously. Okay, so what is this quantity? Well, remember, this is linear in all the 4 variables. So I can expand this. What I get is r of x, y. Is that? No, sorry. I think I spoke too soon. This is not a typo. This is correct as stated. If you plug in t equal to 0, what you get is r, x, y, z, y. It is correct. Okay? Sorry about that. And if I expand the first term in the numerator using linearity, what do I get? I get r, x, y, z, y. That cancels off with r, x, y, z, y. I get 2 linear terms, which is t and then r, x, y, z, w. So the first linear term comes from the tw from the 4th entry, okay? And the second linear term comes from the tw from the second entry, the y plus tw from the second entry of the numerator. So is this okay? So if I expand using linearity in all the 4 slots, the constant term cancels. I get 2 linear terms in t, and then I get a quadratic in t squared, which corresponds to the tw from the second and the 4th slot, but that corresponds to xw, zw. I divide by t, take a limit. So the quadratic term doesn't contribute because when I divide it, there's still a factor of t. As t goes to 0, that goes to 0. So what I am left with is this, okay? It's r, x, y, z, w, r, x, w, z, y. So are there any questions up to this point?
So the fact that we start off with such a f,
Huh.
I mean, is this construction motivated by any way due to the symmetries of the Riemann curvature tensor, or is it just a clever algebraic trick that works out?
Well, so in a way, so it's, as I said, this is not specific to the Riemann curvature tensor. This is specific to any tensor, any like a typical 4-0 tensor, which has the same symmetry as the Riemann curvature. The point being that you want to somehow, so I guess you have to, I don't know of a good motivation, because the result is algebraic, that it somehow you have to combine these things in a certain way so that you can read off the r, x, y, z, w from r, x, y, x, y of various forms, right? So like one example being, if you want like some sort of a like a bilinear, symmetric bilinear form, you can which comes from a norm, for example, you can use the symmetry and you can deduce like quadratic form, you can deduce one from the other, because you can do the q of x plus y minus qx minus qy, and then you take a half, and that gives you the inner product xy, something like that. So this is a more complicated version of that. So we just have to play around a little bit and see which combination of the sectional curvatures work, and this is the one that works basically, as far as I'm concerned. Okay? So I don't know of a good algebraic intuition of why this is what it is, because I don't have any algebraic intuition personally. So okay, so but yeah, but no matter which proof you look at, any proof is going to involve essentially this function, that it's just a way of saying how can you combine the sectional curvatures so that when you expand it all out, you're going to see the Riemann curvature appear as one of the terms. Okay, so yeah, that's my answer. Any other questions? Okay, so yeah, so g prime 0 is this, okay, and you can similarly show that h prime 0 is going to be r, x, y, w, z. So the wz interchanges with zw from the g prime 0, and then rxz wy. So the w and the z has interchanged from g and h. Okay. So whatever was the expression for g prime 0, in h prime 0, you interchange w and z. Okay. Yeah. Any questions? Okay. Fine. So what do we want? We want to calculate 2g prime 0 minus 2h prime 0, right? So let me simplify this for you. I can switch wz back to zw. The price I pay is a minus sign. That is the symmetry of the Riemann tensor. I leave the other one as it is, xzwy. So now you know what to do, right? You have to take this line over here, which is g prime 0, subtract off h prime 0, because there's a minus sign in del f del s. So if I subtract off, I basically get 2 copies of rxyzw, and then minus of zw1. So let me write it down for you. So we conclude that the partial that we want is 2g prime 0 minus h prime 0, which is nothing but 4 times the usual Riemann curvature that we want. These are all at p, by the way. I've skipped that. Plus 2 times rxwzy minus 2 times rxzw. Okay. So what can you apply now? What symmetries can you apply? So there's one symmetry which you haven't applied, namely the Bianchi identity, correct? So let's first of all apply the symmetry of switching x and w, which is the second term. If I switch x and w, the price I pay is a minus sign. So that's already one symmetry that we haven't used. We made use of it now. Now you can apply the Bianchi identity because the y appears on the right. So look at the 2 terms with the negative signs. The y appears on the extreme right, and you can use Bianchi identity because wxz appears in a cyclic fashion. So what should the Bianchi identity give you? It gives you twice rzwxy, correct? But now you can use the only other symmetry that's left. You can switch xy as a pair over zw, and it's the same as rxyzw, correct? So we have made use of all the symmetries crucially, and we have never talked about this being the Riemann curvature tensor. Any tensor having the same symmetries as the Riemann curvature tensor will have the same property. That if you take del 2f by del s del t, this is 6 times the Riemann curvature. Okay, so this is the proof that you can recover the Riemann curvature from the sectional curvature. So any questions or comments? Okay, good. So
Sir,
yes.
sir, why we can't take del 2f by del s del t, not the other?
No, so the point is you can take others also. The point is what do you want? I mean, you want to show that somehow if you have something, this function is clearly determined by knowing all the sectional curvatures, right?
Yes.
And then I'm saying once you know this function, if I calculate this derivative, this is also something hence determined by the sectional curvature because f is determined by the sectional curvature. But this quantity is exactly up to a factor of 6, the Riemann curvature. So when you say I can determine something from something, this is the usual sequence of logic, right? You're saying the Riemann curvature tensor up to a factor of 6 is recoverable from the sectional curvatures by constructing this function and calculating this particular derivative. You can take other derivatives as well, and that will probably give you some other terms, but we don't need it for the statement. I mean, does that make sense?
Okay.
You only want to show that you can recover this. Once you can recover the Riemann curvature, you can recover everything from the Riemann curvature in the obvious way. Okay, so yeah, any other questions? Okay, so this is this is not going to be a computationally useful result, but this is a conceptually good result to have because it's saying you're not losing anything by working with sectional curvatures. You can go back and recover the Riemann curvature tensor, but they look very different. The sectional curvature is something defined on the Grassmannian 2 planes in TM. The Riemann curvature is a big tensor on its own, which is very complicated. Hence, you look for other easier alternatives without losing information. But let me give you a different way to interpret the Riemann curvature tensor. And this is going to be very important for the next lecture in particular, where we talk about scalar curvature and Ricci curvature. So this is again going to start off with linear algebra. Actually, we'll be doing a lot of linear algebra implicitly in this lecture. So you consider the vector space wedge 2 of TPN. Remember what is wedge 2? Wedge 2 is going to be a vector space generated by EI wedge EF, EI wedge EJ if EI is a basis for V or TPN. And wedge simply means that this is the skew symmetric two, like wedge 2 means it's, if you have a vector space V, you can look at V tensor V, and V tensor V splits in two parts. Actually, it splits in two disjoint. I mean, it's a direct sum of two vector spaces. One is the symmetric 2 of V, and the other one is wedge 2 of V. The symmetric 2 of V are the symmetric 2 of V, which means it looks like EI tensor EF plus, EI tensor EJ plus EJ tensor EI by 2. And the wedge look like EI tensor EJ minus EJ tensor EI by 2. So, and this last term we usually denote it by EI wedge EJ. Okay. So this makes sense for any vector space. We're doing it for TPM. TPM is of dimension n. So wedge 2 of TPM is a vector space of dimension n choose 2. Okay. All right. So I'm going to define a bilinear form, which I'm going to call rho of P or rho at P from the vector space wedge 2 of TPM cross wedge 2 of TPM to R. And for those of you who have been following this well enough, you should be able to guess what this could be. So an element of wedge 2 of TPM looks like X wedge Y, where X is an element of TPM, Y is an element of TPM, right? Here wedge literally means X tensor Y minus Y tensor X divided by 2. Same with the other factor, it looks like Z wedge W. So you can take this to be a definition. Take X wedge Y, take Z wedge W, and send it to the Riemann curvature associated to X, Y, Z, W. That's it. Okay. This is almost tailor-made for the Riemann curvature to appear. So there are, of course, there are certain things to check here. So what is that you have to check, and that is an exercise for you. Show that this bilinear form, so you have to show that this is bilinear. That is not too hard to check, but it's well-defined and symmetric. Okay. So once you show that this is well-defined, symmetric is obvious, because to show symmetry, you have to say that if I switch X wedge Y with Z wedge W, the output does not change. But the output does not change if I switch XY with ZW as a pair, simply because of one of the symmetries of the Riemann curvature tensor, right? We in fact used this symmetry just a moment ago. So it's clear that this is symmetric. It is also clear with a little thought that this is bilinear. The only thing you have to show is this is well-defined. And well-defined means, among other things, to show that instead of X wedge Y, if I choose Y wedge X with a minus sign, see X wedge Y is minus of Y wedge X. What should happen to the Riemann curvature tensor? That should pick up a minus sign. But it does, because R of XYZW is minus of R of YXZW, because if I switch X and Y, there's a minus sign. Same thing if I switch Z and W. So you have to check these kind of things. When I say this is well-defined, you have to check these kind of things. Okay? It's similar to the earlier thing that the sectional curvature is well-defined. If I replace X wedge Y with X plus lambda Y wedge Y, the Riemann curvature doesn't change. Things like that. So these are very similar exercises, okay? But check this, show that this is a well-defined bilinear form which is symmetric. Okay. Good. Any questions so far? So keep in mind that this bilinear form could very well be 0. So I'm not at all claiming this is a non-degenerate or non-trivial bilinear form. If we apply this to m equal to Rn, because all the usual Rijkl is 0, this is going to give you the 0 bilinear form on wedge 2 of TPRn. So this could very well be not non-degenerate. Okay. Okay. So this is fine. We have a symmetric bilinear form. Yeah. So this is what I just said. So it may not be positive definite. It need not be non-degenerate. Okay. However, we can talk about a positive definite inner product on wedge 2 of TPM, which is what we're going to get to. Okay. So recall that we have an inner product GP on TPM, correct? So G subscript P is nothing but the Riemannian metric G restricted to the tangent space at P. So using that, I'm going to define an inner product on wedge 2 of TPM, this new vector space. I'll also denote it by GP, by abuse of notation. Okay. How should I define this? What do I have to tell you? I have to tell you, given two elements of wedge 2 of TPM, X wedge Y and Z wedge W, you have to give me a positive definite symmetric inner product. Okay. And I'm defining that to be determinant of this 2 cross 2 matrix. So given X wedge Y, Z wedge W, you calculate GP of XZ GP of XW, GP of YZ, GP of YW. So as before, you can ask, okay, is this well defined? Well, those are things, again, I leave it to you to check. But it's similar to exactly the last exercise. If I replace x wedge y with x plus lambda y y, and you calculate this determinant, the determinant is unchanged. So this is actually a well-defined function, okay? Because you're making a choice, right? Whenever I say x wedge y is the same thing as 2x wedge half y, for example. But if I input 2x and half y in the matrix, I'll get a different matrix, but the determinant is going to be unchanged because the 2 and the half are going to cancel. So that's the point. You have to really take determinant to make this well defined. The matrix itself is not well defined. Okay. I hope this is clear. So this is a pairing on wedge 2 of TPM. Is it bilinear? Well, it is bilinear for obvious reasons. If you scale where x wedge y by lambda, either lambda goes to x or lambda goes to y, but that means either the rows get scaled by y, lambda, or the either one of the rows gets scaled by lambda. So lambda comes out. If I scale z or w by mu, either one of the columns gets scaled by mu, so the mu comes out. So this is bilinear. Why is it symmetric? Is it clear that this is symmetric? Meaning if I switch z wedge w with x wedge y, is the determinant unchanged? So what would be the... So
Yes, because G is symmetric. So
G is symmetry, okay, but is that the only reason, or is the matrix the same? If I calculate GP of z wedge w comma x wedge y, what matrix do you get?
just Z replaced by X and W replaced by Y, and
Yeah, but the symmetry says that the diagonal entries remain the same.
So the matrix remains the same.
Matrix remains the same. Really?
Sir, if you put in z wedge w, x wedge y, GP,
The off diagonal elements perhaps flip.
Exactly, the off diagonal elements flip because you see, so because x, whatever goes in first, x goes in the first row, and then y goes in the second row. So z wedge w, you'll have z comma x, z comma y, and then w comma x, w comma y. So and by symmetry of the metric G, the diagonal entries are going to be the same. The off diagonal entries are going to flip. So you're going to basically get the transpose of the matrix. And just ensure
oh
that
yes,
you know that.
okay, yeah.
However, determinant of A and determinant of A transpose is the same. So again, the determinant is what is crucial. The matrix by itself is not an invariant in any shape or form. Okay. So it is symmetric. Okay. Fine. Is it positive definite? Meaning if I take x wedge y, GP of x wedge y with x wedge y, what do I get? So this is the exercise. So GP is well defined and it's symmetric as the original metric is symmetric. And this is what I was asking. So what is GP of x wedge y, x wedge y? Well, it's simply going to be the square of the area of the parallelogram because you're going to get GP of x, which is mod x square, GP of y, which is mod y square, and the off diagonal entries are just inner product xy, correct? That's it. So this is of course non-zero and it's zero if and only if. So is this clear that if I calculate GP of x wedge y with x wedge y, this is precisely this, okay? Because this is exactly what you get. You get mod x square, mod y square as the diagonal entries and inner product xy as the off diagonal entries. Now note that this is nothing but the area square of the parallelogram. So this parallelogram has area 0 if and only if y is a linear multiple of x. But if y is a linear multiple of x, then x wedge y is 0 anyway. And that is the only way x wedge y can be 0, that y is a linear multiple of x. So we conclude that x wedge y, the absolute value is 0 if and only if x is a linear multiple of y, which is equivalent to x wedge y being 0 itself. So that means the vector is 0, so it is positive definite. Okay, so it is an inner product on wedge 2 of TPM. So let me pause there for a moment and just see if you have any questions. This is quite basic linear algebra, but quite often these things will appear from time to time because you are dealing with tangent spaces, which are linear spaces. It's natural these things will appear. So any questions or remarks? Okay, good. So this is much better. This is not just any bilinear form. This is an inner product, right? Sorry. So I just keep it here. So now we'll go into an even like further digression into linear algebra, and then we'll come back at the end of it with something to take home. We'll come back to this in a moment. The next slide is going to be some more linear algebra. Okay. So keep this in mind. The setup is you have a vector space V, which is wedge 2 of TPM. You have a bilinear form on there, rho of P. You have an inner product, which is G of P. So these are the two constructs that you have on a vector space V. So let's start there. So we have an inner product space over R, V. Our role for V is going to be wedge 2 of TPM. We have a bilinear form B for us, that is going to be rho of P. And then we have the inner product, which is our G subscript P, the new G subscript P, right? Okay. So if I have a bilinear form, that determines the linear map from V to R. How does it do it? Well, the linear map LB acting on the vector W is simply defined to be the bilinear form acting on V, W. Because of bilinearity, this is a linear map, right? Okay, good. On the other hand, you have an inner product. It's positive definite. So it induces an isomorphism between V and V star, and this is something you have seen many times over. V goes to inner product V, dot. Okay. So this is an isomorphism because of the positive definiteness, for example, of the inner product, which says that this map is injective, and because V and V star have the same dimension, an injective linear map is necessarily surjective by the rank nullity theorem. Okay, so we can now use the combination of these two to determine a map from B to V. So given B, you look at the linear map LB, that is an element of V star because it's a linear map from V to R, correct? And V star is nothing but the linear dual of V. So what I could do is I could use phi inverse, which is an isomorphism from V star to V. And I can apply that to the linear map LB, which is an element of V star. And that is going to give me a map from V to V, correct? So is that okay? Oh, sorry, did I say something wrong? Just a second. No, maybe there's a small typo here. So phi inverse is going to take an element of V star. So okay, so forget about this. Okay, so I think this is not what I wanted to say. No, so okay, I don't want to define this from V to V. So my point is that you're going to get, so every B will determine, just a second, what do I want to say here? Okay, sorry. I guess seeing so. Yeah, so there's, I think, okay, so what I said is correct, but I should be a little careful. See, when I said LB, there should have been a secret superscript
LV.
V. Yeah, there should be like a subscript or a superscript little v because LB depends on a choice of V, correct? So fix a vector little v, and then for that fixed choice of little v and the given bilinear form V, you have a linear map LB, which is sending W to the bilinear form V, W. So you have to fix this little v in advance. So for every little v, I'm getting a linear map LBV. So I should have actually noted that before. That's why it was clear in my mind when I wrote this, but it's confused me now. So LB is not really something independent of a choice of a little v. That should be clear because LB depends on this fixed choice of little v. But now when I talk about this, I mean phi inverse of LB little v. So for every little v, you have a linear map LBV. Applying phi inverse, that gives you an element of v itself, because LBV is an element of v star. Phi inverse now gives you back an element of little v, an element of capital V, and that's what I mean here. Okay, so B tilde is really the map phi inverse of so B tilde is really this map, which means if I give you an element little v, you simply send it to phi inverse of LBV. Okay, I hope this is clear. I mean, I think the notation might be misleading, but what I meant is for every v, there's a linear map LB. That's what I meant. Okay, the form B and little v determines a linear map, and so LB secretly is a function of v. Okay, so I input that vector, I get a linear map which is in v star. Apply phi inverse, that's again a vector in v, and that's what I call B tilde. Okay. So any questions about this? Just make sure. All I'm saying is, given an inner product and given a bilinear map, if I have an inner product, the bilinear map can be thought of as a map from V to V. That's all. Using the fact that you can go between V star and V. That's all I'm saying. Right? Okay, good. So our bilinear map was in fact somewhat special. It was symmetric. We're going to make use of that soon. But this is an exercise in linear algebra again. If you can show that if EI is an orthonormal basis of V, then the map phi inverse can be calculated very easily. That phi inverse of a linear functional is nothing but summation, the linear functional acting on EI times EI. So this is an element in V again. It's like EIs with weights lambda EIs. Okay. It's easy to check that this is the inverse simply by plugging in P on both sides. But this also tells you that the right hand side is independent of the normal basis, of the orthonormal basis. If I choose another orthonormal basis Fj's, summation lambda Fj is going to be equal to summation lambda Ei Ei. Okay. So this is a comparison some of you might have seen. I'm pretty sure quite a few will have seen this already. So what do we want? Well, remember our B was symmetric. So we can ask what happens if B is symmetric. Is B tilde somewhat special? So do you guys have any guesses? So if B is symmetric, what can you think B tilde should be? Or is there any particular term that comes to your mind just off the top of your head? B tilde is a linear map from V to V. What are the nice class of maps from V to V?
Orthogonal ones, if
Orthogonal,
it's finite dimension.
Orthogonal is too strong, right? If you just choose a general bilinear thing, it could be the zero thing, right?
Yes.
The bilinear form B could be zero, in which case you expect B tilde to be zero.
So positive semi-definite, we might check.
Positive semi-definite, okay, but something more rudimentary. The self-adjoint would be my guess. I mean, of course, I'm saying that in hindsight because I know what it will be, but you can expect this to be self-adjoint, for example. And in fact, that is true. If B is symmetric, then you just calculate B tilde V comma W. What is B tilde? It's going to be B of V comma EI, where EI is an orthonormal basis, times EI summation. That's what this exercise in red tells you, right? That to calculate B tilde, which is given by the inverse by phi, it's simply going to be this. But what is this quantity? This is going to be, you can pull out the B of V EI and then its inner product EI with W. But the inner product EI with W along with the E can be put inside the rightmost factor of B. So this is nothing but B of VW, right? Because I can now put this scalar in the right factor because B is bilinear. But because it's symmetric, B of VW also equals B of WV. That's why I use the symmetry, which means B of WV also equals B tilde W comma V by the same reason. But the inner product is symmetric. So B tilde W comma V is nothing but V B tilde W. Right? Is this clear? So this tells us that if B is symmetric, then B tilde, the map that I obtained from V to V associated to B, is a self-adjoint map. Okay? Any questions so far? Good. So self-adjoint maps are nice because if we have a self-adjoint operator from V to V, vector space over R, we know that it's going to have eigenvalues, right? Real eigenvalues. So that's going to turn out to be a very useful thing, actually. Okay? So this is the digression on linear algebra. So what this buys us is that in our example, V is wedge 2 of TPM, B is the linear with the bilinear form rho P, and the inner product was GP. So I can trade off the bilinear form rho P to obtain a linear map from wedge 2 of TPM to wedge 2 of TPM, which is self-adjoint. Is that clear? So apply this whole machinery to our example. What we obtain is a self-adjoint linear map from wedge 2 TPM to wedge 2 TPM. Okay. Any remarks or questions? Okay, good. So let's apply this. Applying the preceding discussion to wedge 2 of TPM with the obvious inner product and the bilinear form, we obtain a self-adjoint operator and denoting it by this math cal R, R again for Riemann. This is called the Riemann curvature operator. So this is not really a tensor. This is actually it's a linear operator. And we'll see what relationship it has with the Riemann curvature tensor. Okay. So this is a well-studied object and you can do calculations with it. So let's go back to some examples because it's always good to understand these abstract things in terms of concrete examples. So what happens for a surface? What is wedge 2 of TPM? If TPM is two-dimensional, what is wedge 2 of a two-dimensional space? So what is the dimension of wedge 2 of TPM if M is a surface?
1.
It's 1.
1.
So which means if I choose an orthonormal basis of TPM, let's say E1, E2, then E1 wedge E2 is the basis for wedge 2 of TPM, right? So this is a linear map from one-dimensional space to itself, which means it's determined by a scalar, the value of a basis. Let's see what you have. So consider a surface sigma with local coordinates x1, x2 at the point P, such that del by del x1 and del by del x2 is an orthonormal basis. I'm not claiming this is an orthonormal basis at the local coordinates, but only at P. In general, you cannot have orthonormal basis from coordinate vector fields in a local patch unless the manifold was Euclidean. So this is only at the point P. Okay. So the curvature operator is now going to be determined by the image of del 1 wedge del 2, which means del by del x1 wedge del by del x2 at P. So let's see what we calculate. So remember R of P, what was the definition? The definition was it's going to be you calculate rho of P, the bilinear form acting on the basis E1, acting on the basis EI times EI sum over, but there's no sum. There's only one element, which is del 1 wedge del 2. So it's simply going to be the bilinear form acting on del 1 wedge del 2, comma del 1 wedge del 2 times del 1 wedge del 2. But what is the bilinear form rho P acting on del 1 wedge del 2, comma del 1 wedge del 2? This is simply the Riemann curvature del 1 del 2 del 1 del 2. But because it's an orthonormal basis, this is also the Gaussian curvature, right, which is K of P. So that's it. So the Riemann curvature operator for surfaces is precisely saying that at the point P, it's scaling this one-dimensional space by the Gaussian curvature. So this is one way of recovering the Gaussian curvature in this abstract formalism. Okay? Is this example all right? So the orthonormality is crucial because in general, the Riemann curvature is not the Gaussian curvature. You have to normalize by the area of the parallelogram spanned by del 1 and del 2. But at P, this is a square because it's an orthonormal basis. A unit square has area 1, so you don't have to divide by anything. Okay. Okay. Any questions? Good. So what about another example? So this is an example, I think, more relevant to Ujan's project. So I'll just indicate some of the things. I'll not say much about it. As I'm saying it here because I may not get time to talk about actual computations of Ricci curvature in the next lecture because I have to talk about scalar curvature. So in any case, consider a manifold of dimension 3. So if you look at the curvature operator RP, that is a map from wedge 2 of TPM to wedge 2 of TPM. So what is the dimension of wedge 2 of TPM for three-dimensional manifold?
It's 3.
It's 3. So because it's n choose 2, right? It's 3 choose 2. So if you have an orthonormal basis E1, E2, E3, the basis for wedge 2 TPM is E1 wedge E2, E1 wedge E3, E2 wedge E3, right? That's it. So it's a map from R3 to R3, and it's self-adjoint, so it has 3 real eigenvalues, possibly repeated. They may not be repeated. Anyway, the upshot is that you can take these eigenvalues, call them alpha, beta. It should have been gamma. I don't know why I called it delta, alpha, beta, gamma. And then you can do whatever you want with it. Of course, taking the sum is an important quantity from the point of view of linear algebra, because the sum alpha plus beta plus delta is also the trace of this operator, right? See, the trace of a linear map is the sum of the eigenvalues, correct? So I'm just taking 2 times that. So this is an important quantity. It's not only important because it's the trace, which is invariant under, because the trace is the trace, right? But it's because this is also an important quantity geometrically. It's called the scalar curvature of the manifold M at the point P. So this controls some aspect of the geometry of M. What it controls, we'll talk about it in the next class. But I wanted to put this example here when we're discussing the curvature operator, okay? Of course, for higher dimensional manifolds, this is a bit hard to say, because then you'll have actually n choose 2 things to n choose 2 things, and whatever eigenvalues you get, they may not individually give you something geometric, but certain combinations are going to be important. So it's better to study something which gives you the geometric thing straight away, rather than going via this path of linear algebra, which will not be a very nice thing to work with in high dimensions. Okay. Okay. So any questions? Good. Okay. So let's move on. So now I want to really discuss some examples. Maybe I'll do a few in the tutorial. So manifolds with constant sectional curvature, meaning that the sectional curvature, irrespective of the 2 plane, irrespective of the point P, is constant. It could be positive, it could be 0, it could be negative, but manifolds with constant sectional curvature have played a fundamental role in the development of this subject, Riemannian geometry. And in fact, one can completely characterize such manifolds, meaning manifolds with constant sectional curvature, in terms of the components, the Riemann tensor components Rij, Kl, where we are working under the assumption that Rij, Kl is with respect to an orthonormal basis E1, E2, En. Okay. So let's do that first, and then we'll come back and discuss some examples. Okay. So if you want to read more about how it has helped the development, you can probably read some of the introductory passages in Ducarmo and also Berger. So I'll get straight into the topic. So here's the proposition. So you start with a point P and you consider the quadrilinear mapping. So quadrilinear simply means it's linear in each of the 4 inputs. I'm calling it R prime P, and this notation here means that it's TPM cross TPM cross TPM cross TPM. I simply didn't have the space to write it because it was going outside the slide. Okay, so that's what it means. And quadrilinear, again, let me remind you, means that it's linear in each of the inputs. And the definition is as given. So you pair X with Z times Y with W, and then you switch. And it's quadrilinear because it's linear in each of the variables, because the inner product is bilinear and every variable appears exactly once in each of the 2 terms. So that's why the linearity in all the 4 inputs. Okay. Okay. So here's the proposition. So the manifold has constant sectional curvature. Let's call this constant K0. Again, let me remind you, constant sectional curvature means K of sigma is K0 for any 2 plane sigma inside TPM for any point P. So this is constant as a function on the Grassmannian 2 plane bundle. Okay, so the claim is that the manifold has constant sectional curvature, call that number K0, if and only if the Riemann tensor Rxyzw is equal to K0 times this new tensor R prime. Okay, so these 2 tensors have to be scalar multiples of one another, and that scalar multiple is the constant sectional curvature K0. So that's a if and only if condition. Okay, very useful and quite strong, as you'll see in some examples subsequently. Okay? So any questions about the statement? I hope this is clear. So, and you can almost guess what we're going to do. See, you have this quadrilinear mapping, and then you're basically going to say that these two are the same up to a factor. So how do you show that two tensors are the same? Well, we're going to go back and use the fact that if we can somehow show that the sectional curvature tensors associated to R and R prime are the same up to a scaling, and because the sectional curvatures recover for you the full curvature or the full tensor, and it recovers in a very precise sense, the full curvature behaves exactly the same way up to scaling for x, y, z, w. That's going to be the method of the proof. We first show that the sectional curvature tensor associated to R is k0 times the sectional curvature associated to R prime. And then R prime and R has the same set of symmetries. So the proof that we just did will say that R and R prime will satisfy this relation. Okay, so that's going to be the method. So let's get into the proof. So before we move, let me leave you with the job of showing that R prime satisfies the same symmetries as R, meaning that if I switch X and Y, this R prime changes sign. If I switch Z and W, it changes sign. If I swap ZW as a pair with XY, there is no sign change, and it satisfies the Bianchi identity, meaning if I fix W, cyclically permute XYZ, it adds up to 0. I mean, in this case, you just have to write it down. It's evident that Bianchi identity is true because the terms will cancel pairwise. There will be 6 terms. And it's clear that if you switch X and Y, the sign changes. And if you switch Z and W, the sign changes. And if you switch ZW over XY, there's no sign change. Okay? So it's a very easy exercise that R prime and R has the same set of symmetries. Okay. So any questions before we start the proof? This abstract way of thinking about curvature and symmetries and so on, this algebraic viewpoint is quite nice and powerful because it helps you prove results which otherwise, if you just try to think of in pure geometric terms, would be very hard. Okay. So anyway, so assume that Kp sigma is K0 for any P and any 2 plane, meaning that the sectional curvature is constant. So let's take any 2 vectors xy in TPM, calculate the R prime tensor. What is R prime? It is xxyy minus xy squared. That is by definition, right? But what is this quantity? We just saw this. This is the square of the area of the parallelogram spanned by x and y, right? Okay. What is RP? What is RP of xy? Well, it's nothing but the Gaussian curvature of the plane sigma times the area squared. Because remember, how did we calculate the Gaussian curvature? The Gaussian curvature was the Riemann curvature tensor xy divided by this volume of the or area of the parallelogram. So the Riemann curvature in turn is going to be the Gaussian curvature times the area of the parallelogram squared. But the area of the parallelogram squared is nothing but R prime. And Kp sigma is independent of P and sigma, that is K0. So what you obtain is that Rp xy is K0 R prime P xy for any 2 vectors x and y in TPM and for any P. Is that okay? So this is the first big step. That this is saying that the sectional curvature for R equals the corresponding sectional curvature for R prime. The sectional curvature for R prime simply being xy. You input xy. So this property is true. And now if you go back to how we deduce the Riemann curvature from the sectional curvature, you can go backwards as well, and you're going to, the proof of the lemma works verbatim for R prime. So you can use that to deduce that the full Riemann curvature R is K0 times the full curvature the full tensor R prime, because they have the same symmetries which you use to deduce the sectional implies the full curvature tensor, or the sectional implies the full tensor. And the proof works as well as R prime as it does for R. Okay. So that's the conclusion, that Rp xy z w is going to be this. for any P and any XYZW, but because these were arbitrary, we have an equality of the tensor. The Riemann curvature is equal to K0 times the tensor R prime. And the converse is pretty obvious, so I'll not prove it. But this is it's a very nice statement. So let me pause here for a moment or two and see if you have any questions. Okay? So if you go back and read the deduction from sectional implies Riemann curvature, we haven't used the fact that R was a Riemann curvature there. We basically use the 4 properties, and so that proof works verbatim for any 4-0 tensor. Okay, so any questions or remarks? Okay, good. So what does this buy us? So we proved something. We proved something. Let me go back and remind you the statement. It says, consider this form R prime, which is not too hard to guess or too bad algebraically. It's perhaps something very natural in a lot of contexts. And somehow you're concluding that M has constant sectional curvature if and only if the Riemann curvature is a multiple of this tensor. Okay, so what does this tell us? So let's apply this in a concrete example and see what we get. So let's consider an orthonormal basis E1 through En of TPM and assume that the sectional curvatures are all K0, constant. This happens by the theorem, by the proposition, if and only if Rijkl, this is simply R acting on Ei, Ej, Ek, En, meaning it's R of Ei, Ej acting on Ek, dot product En. If and only if this is K0 times R prime, but if you calculate R prime, what do you get? It's going to be the inner product of Ei, Ek, which is delta Ik, because it's an orthonormal basis, times the inner product of Ej, El, which is delta Jl, minus the inner product Ei, El, which is delta Il, times the inner product Ej, Ek, which is delta Jk. So you get a very nice description at the end of the day. It's saying that a manifold has constant sectional curvature K0 if and only if the Riemann curvature in an orthonormal basis has this form. But this form is very strict because it's saying if anywhere you want the right hand side to be non-zero, what should happen? I has to equal L, J has to equal K, or I has to equal K and J has to equal L. For any other things, it's going to be 0, right? So what you conclude is that the sectional curvatures at P are the same if and only if Rij and Rijji, these are the only 2 non-zero Riemann curvature coefficients. All the other coefficients which are of the form Ij, Kl and not of this form, Ij, or Ijji, are necessarily 0. I mean, that simply follows by looking at the right hand side, which has 4 delta Ij's appearing, so like 4 Dirac deltas. Okay? This is pretty nice. So you say that a manifold has constant sectional curvature if and only if you take an orthonormal frame at any point, and then the only non-zero curvature, the coefficients that should appear is Rij, which is a K0, and minus of Rijji, I not equal to J. Everything else is 0. So it's a very neat characterization in my mind. So this is simply plugging in when this can be non-zero. So you have Dirac deltas and you can work it out. Any questions? Okay. So let me give you
Sorry, isn't it Kronecker delta?
Kronecker delta. What is Kronecker delta?
So the deltas which you're showing here is actually Kronecker delta, not Dirac delta.
No. So see, this might be just the font. See, what I mean by this delta is delta Ik is equal to 1. If I is equal to k, it's 0 otherwise.
Yeah. So this is the Kronecker delta.
Oh, yeah, you're right. Yes, of course, absolutely. So the Dirac delta is what I think in physics you call the delta function, but in math we call the delta distribution. Yes, absolutely right. Yes, it's the Kronecker delta. Yes, yeah. So my apologies. Yes, correct. So yeah, so it's that delta Ij. That delta Ij is 1 if and only y is equal to j. It's 0 otherwise. Yes. Okay. But nonetheless, so this is the claim that if you have a constant sectional curvature manifold, only special kinds of Riemann curvature coefficients are going to appear. Everything else is 0. Good. So let's take an example. I'm not going to compute this example right now because maybe I'll do this later on in some other context. There's more than one ways to do this, but let's see what it is. So you take a sphere of radius r in Rn plus 1. So this is Sn, an n-dimensional sphere in Rn plus 1 of radius r, and it comes with a round metric, meaning that the Euclidean metric on Rn plus 1 induces a metric on SNR, and it's called the round metric. So you can, if you want, you can use the induced Riemannian metric, use the stereographic projection, or take a normal neighborhood, do all sorts of things. But at the end of the day, you can show that the sectional curvature of a sphere of radius r is 1 over r squared, and this is a constant. Okay, it is independent of the two plane, independent of the point. So this is a prototype for spaces of constant positive sectional curvature. Okay. Let's take another example, and in fact the example is chosen so that we have covered all the bases. We saw that the constant sectional curvature 0, a prototype was Rn. For the positive constant sectional curvature, this is a sphere. And next is the negative version where we take the hyperbolic space. What is the hyperbolic space? Well, let me remind you, it's the hyperbolic space Hn, which is nothing but the upper half plane in Rn, meaning it has coordinates x1, x2, xn, should be x1, x2, xn minus 1, there's a typo, comma y, and y is supposedly the last coordinate such that y has to be bigger than 0. So the usual upper half plane in R2 is the H upper 1, the hyperbolic plane. And there's a metric, the metric is given by y to the minus 2 delta ij. This is again the same Kronecker drill. Okay? So which means gij does not depend on the xi's, but as you go towards the y equal to 0 hyperplane, the metric basically you will take longer and longer time to approach the hyperplane y equal to 0. So it scales in the reverse. So it's 1 over y squared. Okay. We have seen, we have discussed this for the hyperbolic plane. This is just a generalization of that. Again, in this case, one can show, because the metric is so nice, you can even compute everything in terms of the metric and compute the Riemann curvature if you want. It's not that hard. Show that the sectional curvature is minus 1. So this has constant negative sectional curvature. Okay. So, and in general, of course, not every manifold will have constant sectional curvature. It's going to vary, but these are the three sort of extreme models, so to speak. Okay. Okay. Any questions? Okay, good then. So I want to discuss this example of Lie groups, and this is going to be the last bit for today. And I wanted to include this example for two reasons. One is that the students, most of you who have taken differential geometry, have seen a bit of Lie groups when it was taught. And the other reason being Lie groups, they form a very important part of modern mathematics, no matter what stream you come from. And they also appear a lot in physics and geometry. So it's a very important class of examples, okay? So let's start with that. Consider a Lie group with a bi-invariant metric. So remember, bi-invariant metric simply means that it's a metric which is invariant under left translations, which is also invariant under right translations. Meaning that if I wanted to evaluate the dot product of two vectors at a point H, I can simply take the map L underscore G or LG, which is left multiplication by G, and then take the LG star of U, LG star of V. Those are going to now be vectors at GH. I can take the inner product of those at GH, and that should be the same as the inner product UV at H. So that's what left invariance means. Right invariance is defined similarly. Okay? So I'll define it formally. There's a footnote, which is something that you should keep in mind, that not many Lie groups admit bi-invariant metrics. So in particular, excuse me, in particular, non-compact, non-abelian Lie groups do not admit bi-invariant metrics. So So if it's a compact Lie group, it turns out compact Lie groups do admit bi-invariant metrics. That's usually often referred to as the Weil trick, Hermann Weil. And if you have abelian Lie groups, then they usually look like torus cross Rn, and they of course admit bi-invariant metrics. But non-compact, non-abelian Lie groups do not. Okay, so this is somewhat restrictive, but it's still nonetheless very useful. So yeah, compact groups admit such metrics. So left invariance means that if I wanted to, as I said, evaluate the dot product of uv at the point h, it's the same thing as taking the linearization of Lg, acting that on u. So this is now a vector at gh. This is another vector at gh. Take the inner product at gh. Okay. And right invariance means that I could have done the same thing by right translating these vectors by g. So that's what the map RG does. RG means you multiply G on the right, and that's right translation. You can linearize that map and act it on U. This is now a vector at 8G. This is now a vector at 8G as well, and you can calculate the inner product at 8G. So all these inner products are the same if the metric is right invariant as well as left invariant. Okay. Okay, good. So where LG and RG are the obvious maps, the left and the right multiplication. Okay. So any questions about the setup? So what specific examples? So I will not talk about specific examples of such metrics on compact groups, but if you want, you can read it up on your own and think about S3 being the first good example that you can think of. I mean, you can talk about S1 cross S2, S1 as well, but S3 is a compact group because it's SU2, and you can work out what this bi-invariant metric is. Okay, so minus trace of AB. That's going to be a bi-invariant metric on SU2, for example. And everything that I say here will work there. Okay? But I'll not do the examples. Okay. So let G denote the Lie algebra of G. This is traditional. This is math frac G. So what you could do is given X in G, this is a vector in the Lie algebra, and the Lie algebra is nothing but the tangent space at identity. We can extend this X to a vector field on G by left translation, meaning if I wanted to define the vector at, if I wanted to define a tangent vector at the element little g, what I'll do is I simply take d of the left translation, act it on the vector x, and this is going to give me a vector at g. And this is now going to define a smooth vector field on all of g, just by left translation. If you do this for Rn, for example, left translation simply does nothing. So if you have a constant vector at 0, left translation will simply generate the same constant vector field everywhere. That's what left translation is for Rn. Okay. Okay, so starting with a vector in the Lie algebra, you can generate a left invariant vector field to all of G. And for what we talk about in the remaining 2-3 slides, this is only going to be for left invariant vector fields, meaning that it's a vector field which is determined by its value at identity, because every other value at any G is determined by D of Lg of that value, or left translating that value at identity. Okay, so all right. So any questions so far on the setup? Okay, good.
Sir, for abelian Lie groups, the left and the for the left and the right multiplication would be equal, right?
Yeah, so for abelian they're even better, right? So if you know that it's left invariance, then of course it's right invariance.
So what about for normal groups? What if the Lie group is normal?
What do you mean normal?
No, sorry. I mean, I meant a normal subgroup. No, sorry. So is a abelian Lie group compact?
Not necessarily. Rn is an abelian Lie group, right? I just that's why I said Rn. See, vector space is always an abelian. So, but the compact ones are going to be tori. I mean, if you think of connected ones, then yeah, they're going to be basically S1 cross S1 cross S1, some number of copies of them. But those are already not that interesting from the point of view of geometry. I mean, it's probably interesting from the point of view of representations and so on, but from this curvature computations, that's something you can do without bringing in D theory, so to speak, because it's a product. So yeah, but the point is that most of the other things that you will encounter, if it's non-compact, then this example is not going to work. If it is compact, even if it's non-abelian, this is going to work, but that requires a lot of Lie theory, that such a compact Lie group has a harm measure, and then you can average out a thing and make it bi-invariant, and that's usually called the wild trick. And there's a whole bit of theory before you can say there are such metrics, okay? And it's related to semi-simplicity and so on, and it's a whole another story altogether. But for compact groups, this example applies. That's what I wanted to say. So yeah, anything else? Okay, so the exercise for you, and I think I did this in maybe one of the other courses that I was teaching, which some of you are attending. So in any case, if you have an integral curve for x, so x is now, whenever we talk about x, y, these are going to be left invariant vector field. So x is the left invariant vector field, which is determined by its value at E. So I'm going to denote by x both the value at E as well as the left invariant vector field determined by the value at E, by making this abusive notation, which all authors do. So consider an integral curve for gamma. So integral curve gamma for the vector field x. What you have to show is that this integral curve is defined for all t. Usually you can only say by this Picard-Lindlof that it's defined locally, but because of left invariance, you can extend it for all t, and this curve satisfies this property that gamma of s plus t is gamma s times gamma t. Note that gamma s times gamma t makes perfect sense because this is a product happening in G, and G is a Lie group. So this is somehow saying that gamma is a homomorphism from the real line to G. In fact, it's going to be a smooth homomorphism from the group R, comma plus to the group G. And it's initialized at E, meaning that gamma of 0 is E, gamma prime at 0 is X. Okay, that's what this exercise means, that this integral curve actually exists for all times. And it's a homomorphism. Is it clear? Okay. This is a very nice application of left invariance and the initial solution that you get from Picard-Lindlof. So, okay, so such a map is called a one-parameter subgroup. It's called a subgroup because, as I just indicated, gamma is a homomorphism. So the image is a subgroup. Okay. So we're going to make a series of claims. Let me make the first claim. Okay. So I hope all of you guys are okay. So the geodesics initialized at E are precisely the one-parameter subgroups of G. So these are the geodesics for the bi-invariant metric that you have chosen. So for the fixed bi-invariant metric, you look at these one-parameter subgroups. Well, these are nothing but the integral curves for left invariant vector fields. The claim is that these are precisely the geodesics. So that's on one hand very good because you practically know what the geodesics are. It's basically this, the ones generated by the left invariant vector fields. Good. So how do we go about proving this? Well, remember, what is a geodesic? Well, a geodesic is something which satisfies, if gamma is a geodesic, then it should satisfy the equation nabla gamma dot is 0, correct? So here, if I can show that nabla x is 0, where x is a left invariant vector field, then I'm done, because the corresponding integral curve for x is gamma, and I'm claiming gamma is a geodesic. So when I want to calculate nabla gamma dot, this is equivalent to calculating nabla xx along the curve gamma. And if I can show nabla xx is 0 for a left invariant vector field x, I'm done. Correct? And by uniqueness, this is going to be precisely the geodesic. So I'll just prove it one way, that nabla xx is 0, where x is a left invariant vector field. So that's a setup. Okay. Are there any questions or comments? Okay, good. So let's start off with 3 vector fields. They're all left invariant. Y3 you'll see soon in a moment. Let x, y, z be 3 left invariant vector fields, meaning that they're basically determined by their values at E, and then you use left translation. So now I would like to remind you of one of these formulas which looked very big, not too bad, but I had probably told you that we may not see this again, but unfortunately or fortunately we are seeing it again. This is the implicit definition of the Levi-Civita connection that we use in the proof that the Levi-Civita connection was unique. Okay, unique, and it existed. So let delta denote the Levi-Civita connection for the bi-invariant metric. Now I'm going to move on to the next slide. So this was the formula. Okay, so this should ring a bell because we used this formula to define nabla xy implicitly because x was arbitrary, and then we said that defines a connection which is torsion free and metric compatible. So that was the existence part of it. The uniqueness followed just from usual algebraic manipulations. This was called the Causal Identity or the Causal formula, and this is what determines the Levi-Civita connection in terms of a formula. So this is something we had discussed. So now what do I want to do here? Well, I want to plug in z is equal to y and x is x, but all of them are left invariant vector fields. So what do I get if I plug this in? See, what you should note is that what happens to the first term over here. So it is inner product xy, and then you differentiate that function along y. So what is inner product xy? Any guesses? So x and y are left invariant vector fields. Is it a constant, for example?
Yes,
So why is it a constant?
because left invariant, so this is just x at 0 and identity and y at identity
Yeah, so because
value.
they're left invariant, if you want to evaluate xy at g, x that is xg comma yg, but xg is dlg of x0, dlg of y0. But because of left invariance, this is nothing but x at e comma y at e. But that is a constant because x at e and y at e are fixed. So all the inner products that you see in the first line are constants. If x, y, and z are left invariant vector fields, which means when you differentiate a constant along a vector field, those are all zero. So all the first three terms in the first line, they're all zero. All right. I hope this is very clear to everyone. So it's zero. Okay. Any questions? Good. So we are left with three terms in the second line. What are those three terms? Remember, z is equal to y. So I'm looking at twice inner product x with nabla y. But if I put z is equal to y, you see the last term vanishes because the last term is inner product x with Lie bracket y with y, but Lie bracket is Q symmetric. So Lie bracket y is 0, so I only have two terms left, right? And just a second. So why do I have this? Yes. So I probably should have skipped this already because this first term 2yxy, that is going to be 0 anyway. So I'm only left with, anyway, at the end of the day, you basically get this, okay? So what you get is twice inner product x with nabla y is Lie bracket, is inner product of y with Lie bracket xy. The twos cancel because the first term here, twice y xy is 0. Okay? So you get x inner product nabla y is equal to the inner product of y with Lie bracket xy, right? Good. So what we want, well, we want to show that nabla y is 0, correct? To show that nabla y is 0, it suffices to show that inner product x nabla y is 0 for any x. So that means it will suffice to show that the right hand side, which is inner product of y with nabla with bracket xy, that is 0 for any x. Okay. So there's an exercise for you. The exercise is not that hard, but this is sort of one of the main ingredients in bi-invariance. If you really want to understand bi-invariance, this is precisely at the heart of the matter. So bi-invariance of the inner product implies this equality, that if you wanted to calculate the inner product of Lie bracket xy with z, that is equal to the inner product of x with Lie bracket yz. So the way I would like to think of this is you have x and z as the two inputs, and then y can pair with x or y can go on the right and pair with z. And it says no matter how you pair y with an x on the left or like z on the right, they're the same. That's what bi-invariance means in terms of its interaction with the Lie bracket. Okay. So this is an exercise that I would highly recommend people to do. But let's apply this exercise to our setting. Remember, we have y dot Lie bracket xy. So in our setting, we obtain, so what we had obtained earlier was the dot product of x with nabla y was simply the dot product of y with Lie bracket xy. But because of bi-invariance, this is where we use bi-invariance crucially. This does not follow from left invariance. This is nothing but this quantity, right? I can use x on y on the left by taking Lie bracket of yx and then dotting it with y. But what is this quantity? See, the Lie bracket is, I mean, the inner product is symmetric. So I can switch y and the Lie bracket yx, and the Lie bracket is q-symmetric, right? So I can switch x and y, but I pay the price by getting a minus sign. So forget the 0. If I switch y and the Lie bracket yx, it's the same because of the symmetry of the inner product. Then I switch x and y, I get a minus sign. So what do I get? I get the original quantity is equal to minus of the same quantity. But that only means that the original quantity had to be 0 to begin with, correct? So what does this say? So this says that nabla yy is 0 because x was arbitrary. It was an arbitrary left invariant vector field, but you have to only evaluate at a point. So nabla yy is always 0, which means the one parameter subgroup associated to y is a geodesic. So are there any? I'll just pause for a moment. Are there any questions so far? Any comments?
Sir,
Ah.
in the exercise we are using that bi-invariance. Oh,
You have to use bi-invariance. This is not just left invariance. Yes. See, bi-invariance means you have to use right invariance here. Left invariance is not going to really help you much. Because so anyway, just try this. I mean, this is, if you were reading a book in Lie algebra and Lie theory, this is crucially what they use. And if you're thinking of it in terms of geometry, then bi-invariance means what we said. But computationally, that doesn't really help you. What helps you is this identity. So yes, any other questions? Okay, good. So let me go into claim 2, and you'll see that the more we go, the beautiful the results become. So it says that the connection satisfies this. And if you're seeing this for the first time, it's really, really nice, right? It says nabla xy is half of Lie bracket xy. I mean, you cannot get any more beautiful than this in terms of formulas. So this says that the connection nabla y in terms of x or nabla y in the direction of x is just half of the Lie bracket xy, again for left invariant vector fields. So let's prove the claim. So how are we going to prove this? Well, if x is left invariant and y is left invariant, x plus y is also left invariant, correct? So by the first claim, nabla x plus y acting on x plus y is 0. But I can expand this using linearity in both the variables. What do I get? I get nabla xx, that is 0. Nabla yy, that is 0. And there are the two mixed terms, which is nabla xy plus nabla yx. And that should add up to 0, correct? Okay, so at this point, you should ask, we haven't quite made full use of nabla being the Levi-Civita connection. In the sense we have, but we haven't used many of its properties, metric compatibility, torsion free. So what is the relevant property that we can use here?
torsion free.
Torsion free, okay. So if I use torsion free, then torsion free means what? Nabla xy minus nabla yx is Lie bracket xy. So on the one hand, the sum is 0. On the other hand, the difference is the Lie bracket, which means that nabla xy has to be half of xy and nabla yx has to be half of yx, right? So that's it. So torsion free tells you that claim 2 is true. So it's a short proof, but it's a nice proof that you see how the Lie bracket and all the Lie structures come into play. Okay. Now we're going to move on to claim 3. So claim 3 is saying that the Riemann curvature Rxy acting on Z is 1/4 Lie bracket xy, the bracket of that with Z, again for left invariant vector fields. Why is this true? Well, again, this is basically a simple computation because you simply compute. So what is Rxyz? Is nabla y, nabla x, Z. minus nabla x nabla y z plus nabla leave bracket xy of z. So let's put it in. So what should happen in the first term? Well, it's nabla y of half leave bracket xy, but that means it's half into leave bracket y of leave bracket xz, correct? Just by applying the formula from claim 2 twice. What about the second term? It's going to be half leave bracket x with leave bracket yz. What about the third term? Well, it's just 1/2 leave bracket xy with z. Okay, so all of this should somehow simplify, which means at some point the Jacobi identity has to come into play because we are seeing brackets of three things, right? So in my point being that in all the claims, the proofs are almost self-dictating in a certain sense. I mean, there's not much room for anything else. So let's change the first one. I can switch x and z, and the price is a minus sign. Let's keep the second term as it is, and the third term as it is, okay? So now you see, if I compare the first two terms, I can apply Jacobi identity because yzx appears exactly in the cyclic order, right? Yzx, x, yz, and then the other term is going to be zxy, yeah. Okay. So yeah, so by the Jacobi identity, you're going to get, well, so you're going to get minus 1/4 zyx, and then you add the half, you're going to get this, okay? So use Jacobi and then simplify. So that's it. So if you use Jacobi, you're going to get 1/4 zxy. Then you have a half, but then you have to switch x with the z. That gives you a minus sign. So half minus 1/4 is 1/4. So at the end of the day, you get 1/4 leave bracket xy bracket with z. So use Jacobi identity in the penultimate step. Okay. Okay. Everything all right? Any questions or comments? Okay, good. So let me move on. So this is pretty much the last slide. So if x and y are orthonormal, what can we say? So again, orthonormality is a specific choice. It simply means that you do not have to divide out by the area of the parallelogram or the square. The Riemann curvature Rxy is the Gaussian curvature of the two plane. I'll interpret what this two plane thing relates to the Gaussian curvature perhaps in the next lecture. But if I look at the two planes generated by x and y, call it sigma, then the sectional curvature for sigma is given by Rxy, xy. And this is because x and y is orthonormal, so you do not have to divide by the area of the parallelogram. But what is this quantity, right? Remember, this is going to be whatever your z is. You have to take your z has to be x, which means you get 1/4 leave bracket xy x, and then you have to take the bracket of that with y, correct? So you can check that if you do this, you're going to simply get 1/4 the absolute value of leave bracket xy square. This is, I mean, this is almost a one line or half line computation once you have the Riemann curvature tensor. The Riemann curvature tensor is already calculated. So this is nice, correct? So let me just end here with a comment. This is nice because it's saying that the sectional curvature is always non-negative for a Lie group which has a bi-invariant metric. This is not always going to be true for a general Lie group. Sectional curvatures could be all sorts of things. This is saying the sectional curvatures are non-negative, and it is 0 if and only if the Lie bracket xy is 0. It's a very nice criterion. So you can use this now, for example, to apply this for S3, which is SU2, and show that SU2 has constant sectional curvature 1. If you choose the metric appropriately, or constant sectional curvature k square if you scale the metric. Okay? So we might see this Lie group example appearing again in the Ricci curvature part, but if I do not get there, I wanted to put this in the computation. So yeah, so that's it. So if you have any questions, I'd be happy to hear them. So I think some people dropped off at the last 10-15 minutes. I don't know if it is due to the wind or the internet failure. But yeah, any questions or comments or remarks? Okay, if not, then